Alright, on to this one. So prove that the set of prime ideals of a ring has a minimal element with respect to inclusion. So this is going to be another typical like Zorn's lemma type argument. A lot like the proof that that the set of with maximal, the set of ideals, any non-empty set of ideals has a maximal element. So this is similar but with prime ideals. And so basically it's going to be very similar, but all the inclusions are going to be reversed. But instead of looking at the union of the prime ideals as we did when we had like an ascending chain, we're going to look at the intersection. And in order to get this to do this intersection to work the way we need it to, we're going to need to use primeness. So let S be the set of prime ideals. It's non-empty since it contains 0. Let S be partially ordered by inclusion. Now we're going to say that A is less than or equal to B with respect to this partial order if A contains B. So the inclusion is sort of flipped from what you would normally think of it, because what you want to do in Zorn's lemma is prove that every chain has an upper bound. And for here, an upper bound is we're going to want something that is contained in everything in the chain. So let P0 contained in P1 contained in blah 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 be a chain in S. So remember, this means that P0 is less than or equal to P1 with respect to this order and blah, 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 blah. So anyways, let P be the intersection of these ideals. Clearly, it's an upper bound for the chain because it's contained in every single Pi. And so that's what it means to be an upper bound with respect to this partial order. Next, I claim that this is the real key here, is that this intersection is actually contained in the set S, i.e. it is, certainly it's contained in each Pi, but the fact that it's an element of S is not obvious, because we know it's going to be an ideal, because we've talked about before how intersections and unions of ideals will be ideals, and if it's not obvious, the fact that an intersection of ideals is an ideal, the proof will be like pretty much exactly the same as the proof that the union of ideals is an ideal. But anyways, so what we really need to prove here is that this intersection P is prime. So suppose we have two elements, X and Y in P. Nope. We want X times Y to be in P, not X and Y in P. Alright? And so suppose that this product X times Y is in P, but X is not in P. We want to prove that Y must be in P. That's what it means to be prime. So if X is not in P, then there must be some J in this intersection such that X is not in Pj. But because these are inclusions, if X isn't in a particular Pj, then it can't be in any of the other Pn's for n greater than or equal to J, because if X were in Pn, then the fact that Pn is contained in Pj implies that X is in Pj. Alright, so now for any n greater than or equal to J, by primeness, you have, what was I doing here? For any n, for any n, xy is in Pn, this product x times y, and x is not in Pn, but Pn is prime, and so y is in Pn. So if n is greater than or equal to j, then y is in Pn. So then what about n less than or equal to j? Well, since y is in Pj, we know by inclusion that, well, Pj is contained in Pn for every single n less than or equal to j, and so in particular y must be an element of Pn. So we've proven that y is in Pn for every single n greater than or equal to 0, which means that it's in the intersection of all the Pi's, which is P. So yeah. So therefore P is an S because it's prime, because if you have a product in there and one factor is not in there, then the other factor must be in there. Okay, so then every chain of S has an upper bound. We know by Zorn's lemma, and S is not empty, we can use Zorn's lemma to conclude that S has a maximal element with respect to this partial order. And maximal elements with respect to this partial order are precisely minimal elements with respect to inclusion, and so indeed the set of prime ideals of a ring has a minimal element with respect to inclusion, and that finishes this proof.